Bismillahirrahmanirrahim. Today we are going to discuss chlorofluorocarbons with reference to environmental chemistry. Chlorofluorocarbons and hydrochlorofluorocarbons are fully or partly halogenated hydrocarbons that contain only carbon, hydrogen, chlorine, and fluorine. They are produced as volatile derivative of methane, ethane, and propane. In this regard, they are also known as haloalkanes. Chlorofluorocarbons are more specific of haloalkanes. They are commonly known by a trade name freons. Charles Kettering, Vice President of General Motors Research Corporation, was seeking a refrigerant replacement that would be colorless, odorless, tasteless, non-toxic, and inflammable. He assembled a team from 1930 to 1935. They developed Freon 11, Freon 12, Freon 113, and Freon 114 through kinetic chemicals, which was a joint venture between DuPont and General Motors. In 1928, they improved the synthesis of chlorofluorocarbons and demonstrated their usefulness for such a purpose and their stability and non-toxicity. Kettering patented a refrigerating apparatus to use the gas. This was issued to Frigidaire, a wholly-owned subsidiary of General Motors. Chlorofluorocarbons are a group of synthetic compounds containing atoms of elements fluorine, chlorine, bromine, and iodine. Their most common forms are number 1 CFC11 Freon 11, number 2 CFC12 Freon 12, number 3 CFC113 Freon 113, number 4 CFC 114 Freon 114. Chlorofluorocarbon or CFC12 and other chlorofluorocarbons are rapidly developed for other industrial applications and widely distributed as commercial products. Now let's look at Freon 11. Freon 11 or CFC11 is also known as chlorofluorocarbon. Its IUPAC name is trichlorofluoromethane. It is colorless, faint ethereal, and sweetish smell liquid that boils around room temperature. Because of its high boiling point, it can be used in the system with a low operating pressure. Trichlorofluoromethane is used as a reference compound for fluorine-19 NMR studies. The molecular weight of Freon 11 is 137.4 and its boiling point is 74.7 Fahrenheit. By January 1, 2020, the production and use of even this refrigerant has to be stopped completely. Now here is Freon 12. Its IUPAC name is dichloro-difluoromethane. It is a colorless gas usually sold under the brand name of Freon 12. It is used as refrigerant and aerosol spray propellant. Compiling with the Montreal Protocol, its manufacture was banned in developed countries in 1996 and in the developing countries in 2010 due to the concern about its damaging effect on the ozone layer. Freon 12 only allowed to use as a fire retardant in submarines and aircraft. It is soluble in many organic solvents. Dichloro-difluoromethane was one of the original propellant for silly string. Now here is Freon 113. IUPAC name of Freon 113 is 112-trichloro-122-trifluoroethane. It is also known as trichloro-trifluoroethane. You can see its formula at the rightmost corner of the slide. This colorless, volatile liquid is a versatile solvent. It has attracted much attention for its role in the depletion of stratospheric ozone. Atmosphere levels of CFC 113 has remained at about 80 parts per trillion since the year 1990s. CFC 113 was one of the most heavily produced chlorofluorocarbon. In 1989, an estimated 250,000 tons were produced. The Montreal Protocol in 1987 called for the phase-out of all CFCs, including CFC 113, by 2010. It has been used as a refrigerant, aerosol propellant, and a cleaning agent for electric and electronic components. CFC 113 is one of the three most popular CFC, along with CFC 11 and CFC 12. When compressed, the gas heats, and when it is expanded, it cools. CFC 113 is of low flammability and low toxicity. This makes it ideal for the use as a cleaner for delicate electric equipments, fabrics, and metals. Now here is Freon 114. Its IUPAC name is 1,2-dichlorotetrafluoroethane. It is also known as cryofluorine. Its primary use has been as a refrigerant. It is a non-flammable gas with a sweetish chloroform-like odor, with the critical point occurring at 145.6 degrees Celsius temperature. When pressurized or cooled, it is a colorless liquid. It is listed on Intergovernmental Panel on Climate Change's list of ozone depleting chemicals and is classified as a Montreal Protocol Class 1, Group 1 ozone depleting substance. When used as a refrigerant, CFC 114 is classified as a medium pressure refrigerant. The United States Navy uses CFC 114 in its centrifugal chillers in preference to CFC 11 to avoid air and moisture leakage into the system. Classes of compounds of chlorofluorocarbons. Chlorofluorocarbons which derived from methane and ethane. These compounds have the formula as shown in purple color, and here is M is non-zero. Hydrochlorofluorocarbons, when derived from methane, ethane, propane and butane, these compounds have the respective formula as shown again in the purple color, and here is again M is non-zero. In the formula shown in the purple colors, here is M and X and Y are non-zero, and bromofluorocarbons have a formula similar to the chlorofluorocarbons and hydrochlorofluorocarbons, but also include bromine. According to the nomenclature, a special numbering system is to be used for fluorinated alkanes. Prefixes with Freon, R, CFC and HCFC, where the rightmost value indicates the number of a fluorine atom. The next value to the left is the number of a hydrogen atom plus 1, and the next value to the left is the number of carbon atom less 1, which means that it cannot be equal to 0, and the remaining atoms are chlorine. Freon 12, for example, indicates a methane derivative only 2 numbers containing 2 fluorine atoms, the second 2, and the no hydrogen 1 minus 1 is equal to 0. Okay, so it is represented as CCl2F2. Another equation that can be applied to get the correct molecular formula of the chlorofluorocarbons are or freons class compounds is to take the numbering and add 90 to it. The resulting value will give the number of carbons as the first numeral, the second numeral gives the number of hydrogen atoms, and the third numeral gives the number of a fluorine atom. The rest of the unaccounted carbon bond are occupied by the chlorine atom. The value of this equation is always a three-figured number. An easy example is that of chlorofluorocarbon 12, which gives 90 plus 12 is equal to 120, 1 carbon, 0 hydrogen, 2 fluorine, and hence the 2 chlorine atom, resulting in CCl2F2. The main advantage of this method of deducing the molecular composition in comparison with the method described in the paragraph above is that it gives the number of carbon atom of the molecule. Freons containing bromine are signified by the 4 numbers isomers, which are common for ethane and propane. Derivatives are indicated by the letters following the numbers. Now let's have a look at the journal structure of chlorofluorocarbons. As in simpler alkane, carbon has tetrahedral symmetry. The fluorine and chlorine atoms differ greatly in size and effective charge. The methane-derived chlorofluorocarbons deviate from the perfect tetrahedral symmetry. So, the physical properties of chlorofluorocarbons and hydrochlorofluorocarbons are tunable by change in the number and identity of the halogen atoms. In general, they are volatile but less than their parents from which they are formed. This decreased volatility is attributed to the molecular polarity induced by the halide, which induces intermolecular interactions. Now let's have some general properties of chlorofluorocarbon and hydrochlorofluorocarbons. Number 1. Chlorofluorocarbon and hydrochlorofluorocarbon are inflammable. Number 2. Chlorofluorocarbon and hydrochlorofluorocarbon are volatile, but they are less volatile than the parent alkane from which they are formed. Volatile means the compound which evaporates at normal temperature. Number 3. Decreased volatility is attributed to the molecular polarity induced by the halides, which in turn induces intermolecular interactions. So in this way, methane boils at minus 161 degrees Celsius temperature, whereas fluoromethanes boil between minus 51.7 to minus 128 degrees Celsius temperature. Number 4. Because of polarity, chlorofluorocarbons are useful solvents. Number 5. The densities of chlorofluorocarbons are higher than their corresponding alkanes. In general, the density of these compounds correlates with the number of halides. Number 6. Chlorofluorocarbons and hydrochlorofluorocarbons are usually produced by halogen exchange starting from the chlorinated methanes and ethanes, as it is shown in the following reaction that chlorofluoromethane was synthesized from chloroform. Chlorofluorocarbons replacement. Chlorofluorocarbons have many industrial uses, but in this section the focus will be on the use of CFCs as a solvent and the research for potential solvent substituents. Chlorofluorocarbons are used extensively in the electronic and aerospace industry to clean metal parts. Their chemical inertness ensures against the damage to the surfaces to be cleaned, and their relatively high vapor pressure makes drying the surface after cleaning simple. More precisely, chlorofluorocarbons were used extensively, frequently as replacement for other chlorinated solvents. In fact, between 1974 and 1985, use of chlorofluorocarbons as a solvent tripled, largely because of these environmental concerns about other solvents. The most common method for finding CFC substitutes has been to simply compare the desired properties of the CFCs to the properties of the list of the potential substituents. When chlorofluorocarbons are used as solvents, particularly for solubilizing hydrocarbon greases absorbed onto the metal, the target properties are solubility parameters compatible with the long chain hydrocarbons, low flammability, and a boiling point slightly above the room temperature. Unfortunately, the racking potential of the chlorofluorocarbons replacement from a definite list of the solvent will not lead to the best replacement. A more systematic approach to engineering a solvent replacement is afforded by thermodynamic group contribution method. Most uses of chlorofluorocarbons are now banned or severely restricted by the Montreal Protocol of August 1987. As they have been shown to be responsible for ozone depletion, brands of freon-containing hydrochlorofluorocarbons instead have replacing many uses, but they too are under strict control under the Kyoto Protocol, as they are deemed super greenhouse effect gases. Because chlorofluorocarbons, they are also under the Kyoto Protocol, because Kyoto Protocol is about the greenhouse gases. Here is air pollution control priorities and methods. Reduction of the chlorofluorocarbons has been achieved at the front end by stopping production of these chemicals, and at the end of life by capture and reuse. While these measures were introduced primarily to help preserve the ozone layer, they are also helping to reduce global warming. The atmospheric concentration of chlorofluorocarbon 11 and chlorofluorocarbon 12 are 6 orders of magnitude less than the carbon dioxide. However, they are estimated to have about 1,000 times the global warming effect per molecule of carbon dioxide. In other words, we can say that each molecule of chlorofluorocarbon 11 and chlorofluorocarbon 12 that is prevented from release to the atmosphere reduces the potential global warming effect by 1,000 times than that of the molecules of carbon dioxide. In the early 1980s, 1.5 million metric tons of CFCs were being produced annually. On release, this would have contributed a GWP on the equivalent of about 1.5 billion metric tons of carbon dioxide. Let's have a look at the amazing aspect of chlorofluorocarbons, and that is the stability of chlorofluorocarbon. When scientists discovered a depleted stratospheric ozone, chlorofluorocarbons were identified as the culprit. Chlorofluorocarbons are highly stable and inert chemicals with corresponding long residence times. For example, CFC11 has an atmospheric lifetime of 60 years. CFC12 may remain in the atmosphere for 120 years. CFC113 has an age of 90 years. CFC114 has a life of 200 years. The atmospheric concentration of total chlorofluorocarbons in the early 1990s was about 0.7 parts per billion and was increasing about 5 to 6% per year. Because of the continued releases from CFC containing equipment and products already in use, CFC emission to the lower atmosphere have continued since their manufacture was banned in 1990. However, chlorofluorocarbons concentration in the troposphere declined in 2000 for the first time since the compound was introduced. Model calculations show that it will take 20 to 40 years to return to pre-1980 level.
Hi everyone, in this video we are going to discuss chlorofluorocarbons, also known as CFCs. So chlorofluorocarbons is quite the mouthful, so most of the time when people refer to these molecules, they are calling them CFCs. So let's break it apart because it is quite complex. Chloro comes from the element chlorine, fluoro comes from fluorine, and then carbon, that's a tricky one, but I bet you got it, that comes from carbon. So before we move on, I want to ask you a quick review question. What group are both chlorine and fluorine in? I don't want a number, I want a name of the group. Go. Alright, if you said halogens, you are definitely correct. Chlorine and fluorine are definitely in group 7, also known as the halogens. Now, back to CFCs. There are two CFCs that I absolutely expect you to know. They are called Freon 11 and Freon 12. So Freon 11 has a carbon in the middle. It has one fluorine. Okay, and I'm going to draw in my lone pairs just so you know and kind of get used to them, but make sure you're doing this when you're drawing out your Lewis structures. It has 3 chlorines. So one carbon, 1 fluorine, and 3 chlorines. Now, this one that I just drew out, this one is called Freon 11. So Freon, F-R-E-O-N 11. Now, we also want you to know Freon 12. So Freon 12 has 1 carbon, but it has 2 fluorines and 2 chlorines. Now, does it matter how you draw this out? Can the fluorines be next to each other? Can they be across from each other? Yes, it 100% matters. You must draw the fluorines next to each other and the chlorines next to each other. If you draw the chlorines opposite of each other in the transposition, you change the polarity, you change the reactivity. So you absolutely need to understand that Freon 12 looks like this. The fluorines are next to each other, chlorines are next to each other. Now, let's talk about CFCs. One of the most important things you need to understand, CFCs are not natural. They're not natural. So what does that mean? What do I mean when I say that? You are never going to find a CFC out in the atmosphere that just existed, that like a plant created it or it's there. You are only going to find CFCs that someone has synthesized in lab. A chemist has been there, they've mixed some stuff together, and they created a CFC. But CFCs do not exist naturally on this planet. So why did we invent them? Well, in the 1930s, we had serious issues with our refrigerators. We were using toxic gases, ammonia, and SO2. So think about this. In your fridge where you put your food, we are using toxic gases to keep the fridge cool. It was a big problem. So what happened is we invented these CFCs right here, okay, these CFCs as an alternative for these toxic gases. So why did we use CFCs? Well, here's some important things. First of all, they're non-toxic, so that's great. We definitely want non-toxic things in our fridge. They're odorless, even better. They're colorless, which is great. And I think this one's even more important, they're inflammable. So you no longer have this refrigerator that's toxic that could potentially catch on fire. So in other words, these are stable molecules. Some of them, not all of them, could actually last for 120 years in our atmosphere. That is a long time. So you have to think about that. In the refrigerator business, these people are super ecstatic that they invented a gas that is so stable that they could put in the fridge and the fridge will last. So they make quality products. products. Now, in the 1960s, the CFCs really took off because we learned that we could put CFCs in air conditioning or in air conditioner units. So think about this. People down in Miami all of a sudden can have an air conditioner and they're happy. And so what's really neat, actually, and people don't realize this, is CFCs, which really is actually air conditioning, helped so that people would actually move down to the south. And so it's kind of neat. CFCs are yay, except for the fact that they're not. They're actually really, really bad. But we're going to go into that in just a second. But before I do that, I want to ask you a quick question. We also have these things called halons. Now, halons are like a cousin, maybe, distant cousin, close cousin of a CFC. And so the big difference is that they have bromine in them instead of chlorine. And so CFCs have chlorine, halons have bromine. So let's talk about one specifically. I want to talk about halon 1301, and that has that formula right there. Please draw me the Lewis structure. Go. All right, did we get an answer? Hopefully we did. Let's draw out the structure so that we can just make sure we're all on the same page. So the first thing you do, if you ever see a carbon, try to put it in the center. Carbon wants to be in the middle. Now we have 4 other things, so let's just draw it around there. Here's your bromine, and then we have 3 fluorines. And so I kind of showed you what the structure looked like above when we were talking about our Freon 11. But there you go. There's your halon 1301. So hopefully you were able to answer some questions about that and draw out the structure properly. If you're still stuck on those structures, please go back and review. You absolutely need to know how to do that. All right, moving forward. So now we move to the 1970s. So in the 1970s, there were these 2 really awesome people, Roland and Molina. Now, what they did is they were like, what do you think happens when we take Freon 12, okay? So that has 2 fluorines on it and 2 chlorines on it. This was Freon 12. What happens when we shine light on it? And you're going to see chemists do that. They're always like, what happens if we shine light on it? What happens if we set that on fire? What happens if we blow that up? And so luckily, they just wanted to see what happened when they put light on it. So they put some UV light on it, very high energy, so wavelengths of less than 220 nanometers. And what they saw is that this molecule, so your Freon 12, actually broke apart into this guy right here. So the carbon still had the 2 fluorines on there and 1 chlorine, but it formed these things. What are those called again? All right, hopefully you got that answer correct. It is definitely called a radical. So anytime when we see one unpaired electron on something, we just represent it with a big dot, and that is called a radical. When I say radical, I want you thinking reactive. It is so reactive. So here is what happens when chlorine radical goes into our environment. Number 1, it destroys our ozone. And I'm not using the word destroy because I like to have high energy and get you excited about chemistry. I'm using the word destroy because it actually destroys our ozone. So it takes our ozone molecules, so 3 of them, and converts them to 3 oxygen molecules. Now, how does this happen? Well, it turns out that chlorine radical is actually a catalyst. Now, we've mentioned catalysts before, but just in case you've forgotten, they are something that are consumed, so they're used as a reactant right in the very beginning. And, this is the most important part, they are regenerated. Now, that means they are used up in the very beginning. So here they are as a reactant, they react with ozone, a lot of stuff happens. So this big mechanism, blah, 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 blah. At the very end, it spits out oxygen, but it also creates another chlorine radical. So that chlorine radical runs right back to the top and breaks apart more ozone molecules. Over and over and over again, just one. And it turns out that 1 chlorine radical, just one, can destroy, I'm using the word destroy again, 100,000 ozone molecules. Seriously, think about that. 1 chlorine molecule can destroy 100, I should say atom, 1 chlorine radical can destroy 100,000 ozone molecules. CFCs are so bad for us up in the stratosphere. It's so bad for us. In fact, let me show you this graph, which is called the smoking gun. People started measuring out, like I told you, the ozone concentrations, but they also started measuring out our stratospheric chlorine concentration. So they were measuring this right here, our concentration. And what they saw is that our maps were literally just exactly the same. So we start here pretty flat for our concentration of ozone. All of a sudden we start having an increase of our chlorine. Well, the second we have an increase of our chlorine, we see a huge decrease in our ozone concentration. Then we see a dip off. The chlorine goes a little bit lower, ozone gets a little bit higher. Then we see the chlorine concentration shoot straight up, and oh, same thing. The ozone one gets lower and lower and lower. This graph is called the smoking gun. Let me get rid of it so you can see a pretty thing. This is called the smoking gun graph. Thank goodness this was published, because the world responded in such a beautiful way, and they actually were able to move forward, and we were able to protect our ozone layer. But it was this graph, this one right here, showing how the second you increase your chlorine concentration, we have a huge decrease in our ozone concentration. So just to make sure we're all on the same page, let's make sure we can answer one question together here. As the concentration of chlorine increases, the concentration of ozone, what happens? Take care of yourself, guys. Drink water.